In this video, we're going to talk about the final type of vector that we're interested in being able to compute in this section, and that is a binormal vector. So we've already talked about tangent vectors and normal vectors, specifically unit versions of them represented by t and n. And we talked about this idea actually last time, or in the last video, which was that if I had a curve existing out in 3 space and I had a tangent vector that was on that particular curve, there would actually be infinitely many different normal vectors that I could construct. But n of t was just one of those normal vectors. And let's say for the sake of argument, it's this one here in blue. Well, the moment that I have those two vectors, you'll note that there's kind of automatically going to be 3 distinct points in space that I have identified via those vectors. And once I've done that, I know that 3 vectors determine the equation of a plane. Okay, so once I have 3 points out in space, there's a unique plane that kind of contains those particular points, assuming that they're not all collinear, which in this case they would not be. So this plane right here is what we refer to as the osculating plane. So it's kind of like a plane that's in some way that is determined or containing these 2 vectors. One of the things that's interesting, though, is that when we think about a plane, we often thought about writing the equation of a plane by establishing a point and also having a vector that would be normal to that particular plane. And this is exactly where our binormal vector b of t comes in. Let's go to the definition below. If c is the graph of a vector valued function in 3 space, we define the binormal vector at t to be b of t, and it can be found by taking t of t and crossing it with n of t. Now, I guess technically the way that I drew this up above in the picture wouldn't quite make sense, because notice here that the order of this cross product requires that I would start at t and then curl to n. So that would actually mean that I would have a vector here, b of t, that's pointing downward by the right-hand rule. So I'll adjust that in my picture. But one of the things that's kind of interesting is to note that this here is already a unit vector. And we're going to take a look at example 3 to actually go ahead and attempt to prove that. Okay, so let's take a look here. If I wanted to show that I have a unit vector, that means that I would want to show that if I calculated the norm of b of t, I want to get to the point where I've established that this is equal to 1. Well, all that I know now is that based on its definition, this is the norm of technically the cross product of these 2 other vectors. But we actually talked back in 1.4, where we discussed cross products, that there was actually a cool formula for what the norm of a cross product could represent. So I'm going to go over here to the side and quickly say, recall that if I had the norm of u cross v, that was equal to the norm of my first vector times the norm of my second vector times the sine of theta, where theta is the angle between the 2 vectors. So since I have the norm of a cross product right here, I'm going to go ahead and use that. So that means that this would be equal to the norm of t times the norm of n times, not the cosine, but the sine of the angle theta that exists between the 2 vectors. Well, let's try to think about what each one of these things here would actually be. Well, what's the length of t of t, the unit tangent vector? Oh, well, it's a unit vector, so its length is always 1, regardless of t. Similarly, the length of the normal vector is always going to be 1 because it's the unit normal vector. And we know that these vectors here were at a 90-degree angle, which means we're going to have the sine here of pi over 2. We know that the sine of pi over 2 is equal to 1, and so the grand total of this is actually just 1, which means that the length of this vector is 1. And so we can say that b of t is a unit vector. Okay, so if I actually wanted to calculate b, this binormal vector at any point in time, notice that I gotta calculate t and then I also have to calculate n, which means I have to do a lot of work here to actually get this. Now, sometimes you can think about the way that a problem might be written. For example, if I had part A in a problem, find t of t, part B in a problem, find n of t, and then part C in a problem was like find B of t, maybe then using this definition to calculate it wouldn't be so bad. But if I had an example kind of like what I had here, and it said find me the binormal vector for this function at this point in time, that can actually be extremely cumbersome to calculate. And we'll actually then have to, or this serves as motivation for how we might want to try to come up with a shortcut for this, and we'll talk about that in the next video.